Welcome, and thank you for joining us for this webinar presentation. We are the Defense Systems Information Analysis Center, or DSIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports those working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the defense systems DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD defense systems research.
Hello, everyone. Welcome. Thank you for joining our webinar this morning, afternoon, evening, wherever you are, what time it is. My name is Taylor Knight. I am the DoD IAC Technical Inquiry Research Services Lead. So I'll be kind of your host for today. We're very happy to have Matt here for this presentation. Before we get started with his wonderful information, I just have a couple things that I wanted to go over to share with you, some housekeeping issues. Before we start, if you do have any questions during this time, please use the Q&A section instead of the chat. It's just a little bit easier for us when we moderate. We'll have an entire Q&A session afterwards. You can find the Q&A forum using, there's like an ellipses, the 3 dots, probably near the bottom of your screen. It might look different on your end, but it's different in the chat and you can type it in there. We'll go over all the questions after the presentation is complete. Also, if you have any technical issues, this is being recorded, so you can catch up later. You can download the slides. We'll have the slides up on our website at dsiac.org, or we have a webinars page on our YouTube channel as well. Finally, as mentioned in our video, one of the main services that the DSIAC offers is, since we're an information analysis center, we offer a free technical inquiry research service. We are fully funded to help answer any questions you might have that stem from Matt's webinar in the domain of AM or really any other of our focus areas that you can find on our website. We offer 4 free hours of this research to help jumpstart you on your research, on any questions you have, on any science and technical information that you're looking for. So at this time, I'm going to pull up Matt's presentation and I will hand it over to him. He will introduce himself. We'll go over his background, we'll dive into the presentation, and then we will have a good 15, 20 minutes-ish, depending on the length of the presentation at the end, where Matt will go over and answer any questions that you have during this time. So I'm going to pull up his presentation for everyone, and then I'll hand it over to you, Matt. It should be loading. You should have control now, Matt.
All right, I'm all set.
Great.
Ready?
Yeah, go for it.
Okay, great. Yeah, thank you everyone for coming in and joining me. Really appreciate taking time out of your day to watch my presentation and some stuff about metal 3D printing. So what my topic is integration of shipborne additively manufactured systems onto naval vessels and the naval supply chain impacts. So that's a big, long DoD kind of title for we want metal 3D printing on naval ships to basically increase the readiness, increase the supply chain, and also help with obsolescence and spare parts. So we'll jump right into it here. So who am I and why am I qualified to talk about this? So I'm a mechanical engineer from South Dakota School of Mines and Technology. And my first internship was with Naval. That's basically the Navy's Air Force. And that was the first place I got introduced to 3D printing and metal 3D printing. So I was lucky enough to be, while I was an intern, I still participated in the first ever 3D printing of a titanium critical part on the V-22. So that was a lot of fun to be a part of that and just see that whole process. And then I have a couple years experience working for different metrology companies and software companies. And really what has kept me interested in 3D printing is I'm a hobbyist, like probably a lot of yourself with 3D printing. It's a lot of fun. So I can't quite afford a metal 3D printer at the current moment. So I just have the polymer 3D printers. So just plastic, FDM, and resin printers, and do a lot of 3D modeling on the side as well for fun and other little projects here and there. Yeah. So what we're going to go over today is the promise of AM. So what is it kind of prophesized to help out with, solve problems, and what's the goal of getting AM on the ships, or really AM in general? And I'm going to be using AM and 3D printing interchangeably during this presentation. So really AM stands for additively manufactured. Also, I'm going to be kind of talking at the level that you do know what 3D printing is and kind of have an idea of how it works. Not, you don't have to go into full detail, but if you have any questions, please add them into the chat there. I'm sorry, the Q&A. And then so getting, and another caveat for this presentation is that I do just want to focus on metal AM for Navy ships. And this one, I wanted to do that because if we talk about polymer as well, I think that's going to be a very long presentation, and that would definitely be, in my opinion, another presentation. So I just want to focus on metal 3D printing and metal AM. So getting a metal 3D printer on a ship, that's going to have a lot of challenges. It's a challenging thing to do in a laboratory setting. It's taken quite a while to get something, get to where we are now. And then I'll be also talking about the current state of metal AM on ships. So right now we have two metal 3D printers on two different ships, the USS Baton with the metal 3D / Haas hybrid system. And then we have the USS Essex, which has the LMX by Xerox. And then we'll be touching on the future impacts and foreseeable future of metal in the AM. All right, so the promise of AM. So in the last 10 or 15 years or so, additive manufacturing and 3D printing has really had a renaissance since its invention in 1986, to where you have it's the technology has gotten small enough and cheap enough that really when it first came out is really only accessible to large companies with high budgets and lots of floor space. And then if you go on Amazon right now, current state, you can get a decent plastic printer for $100 and it shows up at your house tomorrow. And then you can, watch a million YouTube videos on how to 3D print and do whatever you want. So it's come down to technology has gotten smaller, gotten more precise. Materials have exploded. There are so many different polymers you can use. Metal materials have gotten really extensive too. Inconel, titanium, a whole bunch of different alloys of steel, aluminum, I even believe there's copper as well. So really exploded in that aspect too. And of course, extend those different materials out to different applications in every sector. And then the government has also taken note and seen the impact that additive manufacturing can have on the whole, the whole U.S. Economy and industry as a whole. So they've actually spent quite a bit of money to get standards and get technology moving on that, and private investments as well. Lots of companies have seen the same thing. And even old companies like Xerox, like we'll see later, have invested lots of money and time into projects, but also new companies like Metal X or Desktop Metal and stuff like that they've created their own technology and really have come up with new systems. So, and then of course standards, ASTM has been working on standards, and we'll touch on that later, and why that's so challenging. But so we have come quite a bit from we have come quite a long way since its invention in 1986. And since then, naval planners have taken note, and they follow suit with other government bodies and proposing shipboard augmentation of supply departments within AM. So what does that mean? That means that naval planners, they see, okay, great, that hypothetically would be, I'm sorry, in the chat, it says any slides. Can we see that? Can everyone see the slides? I'll just continue until okay, thanks. So that might be on your end. Sorry. Thank you. All right, so I'll just continue. All right, where were we? So naval planners, they have seen, okay, that could be awesome. We could 3D print something in the middle of the ocean, replace a part. We don't need to have spare parts for a certain thing. So there's a whole big avenue to that. So even Lieutenant Scott Cheney Peters, he said, print me a cruiser. Now that's not really capable right now, but the point being is that, hey, if I just have one of these on my ship, that means I could 3D print and do plenty of replacement parts for practically anything, hypothetically. So the benefits of AM on naval ships. So you have two different avenues on that. You have logistics. You got less spare parts. I don't need to have a storeroom full of every single spare part for every single aspect of every system on the ship. I could have powder, or I can have 3D printing feed wire, operational availability, on-demand production, space optimization. So instead of having, like I just said, you have a huge cargo storage of all these different spare parts, I could just have, I mean, you're still going to probably have some spare parts, but you could reduce that significantly by just having the raw materials on the ship itself. And then, yeah, when we're out in the middle of the ocean, you really are by yourself. I mean, you have your ships around you, but emergency resupply or getting spare parts from a resupply station, that's going to take a while. So if I can print something out in the ocean, that would be fantastic. And then obsolescence management, that's a big topic in the DoD right now. Self-reliance and shorten the timeline for different system replacement parts and doing that kind of maintenance as we go. All right. So that all being said, it sounds awesome, and let's put it on all the boats right now, but it's not as easy as that. So there are quite a bit of challenges for metal AM integration. So first off, let's go over what your typical metal AM environment as of the last, I don't know, 10 years has been. So like I said, I personally can't afford a metal 3D printer. They run hundreds of thousands to millions of dollars. So really only larger companies can handle that. And what you need for it is you need ample floor space. Some of these machines can be quite large. You're going to need room for the machines. You're going to need rooms for the material storage. You're going to need some sort of safety precautions in place, evacuations, whatnot. These rooms need to be climate controlled. So, and that doesn't necessarily mean keep it at 65 degrees, but what I mean by that is that temperature, humidity, it's all going to be somewhat consistent day to day. Like you're not going to have a lot of changes in between your different day-to-day operations. So if I print something in one exact way on Monday, print the exact same thing with the same parameters, it's going to be, you would assume that it's all going to be the same on Friday. And then cleanliness control. So that means, you know, you're going to have, it's going to be as clean as a laboratory can be. So that's always a plus there. You're not going to have foreign materials. And then storage space, it's on, you know, you're on land, you have plenty of space, you're fine with that. There's evacuation available. That's fine. If you look at that picture I have there, I guess I'm sure they have an evacuation plan hypothetically, but if you were to have some sort of disaster or situation and you need to evacuate right now, I see plenty of doors, plenty of open air to get out of there. And some of the materials the raw materials that you print with, they are hazardous to you. So having that PPE, having some of the safety precautions in place, that's all available in a normal lab setting. And then, all right, so how do I transfer that 3D printing in the lab space to out in the open ocean? There's some difficulties and conditions we have to factor in here. So ocean factors, I've spent a good amount of time out in the open ocean as a ship's engineer for private vessels. So, and I'm sure a few of you are Navy or Marines or Coast Guard out there. And so you can attest to me that the ocean can be beautiful, but it can also be unforgiving and treacherous at times and with little warning. So some of the big things, especially when I was with the Navy, we heard quite a bit about salt fog and corrosion, kind of the bane of a lot of the existence of the systems out there. And so if you don't know what salt fog is, it's kind of the salty sea gets atomized and will deposit on ships and aircraft and stuff like that, and it will corrode. Combined with the high humidity, it will corrode things a lot quicker than normally anticipated. You have inclement weather, storms, large waves, motion of the ocean. Even if it's still a little bit, even if there is no storm, you still have those rolling waves and you're going to get up and down motion. Excuse me. So what does that do to our 3D printers, or what could that do to our 3D printers? Salt fog could damage a lot of those delicate components. There's a lot of moving parts on 3D printers. And then the motion of the ocean or inclement weather could change powder distribution. Like there is a type of 3D printing where it is what's called SLS, selective laser sintering, and how it works is there's a bed of powder, laser comes by, so it's powderized metal, and then the laser comes by and it will kind of solidify a certain section of it. Next powder comes by, solidifies it again. Now, if that powder changes distribution, even just a little bit from what it's supposed to be, it will damage your parts. It will not have the anticipated values. And then on the shipborne side of things, you need consistent electrical power. So most ships are powered by generators, nuclear, diesel. We want to make sure that power isn't drawn or there are no power blips or reductions in power, because a lot of these systems are laser based. Even a tiny millisecond of power that is lost You may not notice it if you're on your computer or anything like that, but the laser will certainly not melt that little area, let's say, and then you have a small void inside your part. And that's a great stress concentrator, and will certainly reduce the expected strength of your part. And even more kind of scary is that it's a lot of times it's very hard to detect unless you have a X-ray NDI machine. Sorry, the name of it is escaping right now, but basically a X-ray to detect that. And then adjacent projects, other people are doing their maintenance projects, other people are doing their CNC work. You're going to have particulates in the air, vibrations. Like I said, change that can all cause change in deposition rate for material. And then some of the printers I'll go over later do require an inert atmosphere. So they will, just like welding will. So we want to make sure we have that in our atmosphere. And then again, safety concerns. Not a lot of places you can evacuate on a ship, and fire and explosions are certainly two of the most dangerous things you can have on a ship. So like I heard of a story one time where they had a person that was transferring, or I believe it was a cleanup crew at a laboratory for metal 3D printing where they had powderized titanium. He was transferring it from one container to another to dispose of it, poured it over like you're not supposed to do. It kind of turned into powder in the air as he was pouring it down, exploded because of a powderized metal in the air, and made a big explosion. So we definitely don't want to have that on the boat, and that kind of touches into improper training because that was against but he wasn't trained to do what he was doing. So yeah, danger to health, and safety is a big thing, but also there's wasted material. We don't want to waste material when we're out in the middle of Point Nemo or whatever in the Pacific Ocean. All right. And then so I reached out to the Naval Postgraduate School, who was really working hard on this, integrating AM into, or metal AM into ships. And one of their biggest points that they wanted to speak to me about was that it's not just the Navy that is trying to do this. It's really a joint effort between a lot of different departments. So you have Naval Postgraduate School, U.S. Army has their own 3D printing, Coast Guard, Navy, Marine Corps, they're all, but the goal is all the same, is that let's put, the metal 3D printing on a ship is going to be one of the harder environments to do that in. So let's learn as much as we can about, hey, what is it going to actually do? If there's a storm outside, is it going to mess up my print here? That is analogous to, let's say I have a forward operating base somewhere out there. There's a dust storm out there. Is that going to affect my part? It's very analogous, and the whole goal is to have a cross-disciplinary expertise exchange. We're going to learn from other departments' success and failure. So there is a real idea of synergy across the different departments. And then I wanted to touch again on standards, and really the topic of standards for 3D printing is a whole nother presentation. But in general, there's not really an all-encompassing standard for additive manufacturing, because if I were to print a part horizontal versus vertical, they really are going to be two different parts if we look at the structure of it, and like the crystal structure and all that stuff. So it's a very challenging thing to do. All right. So one of the things I learned by talking to Naval Postgraduate School is that at this very moment, the goal of all additive manufacturing on today's ships is for testing. So we're not, at the current moment, the goal is not to, okay, I have a part that's missing on my F-18. I'm going to 3D print that right now. You'll see later there is a case of that or something similar, but really that was an exception. The goal for right now is going to be, okay, I want to know what is going on the ship that affects my parts, and then we're going to gather all that data. It's really kind of a data acquisition. So how they're going to do that is they're going to do what's called the twin experiments. So Naval Postgraduate School has taken, I believe, the LMX printer, and I'll talk about that later. And they have printed a series of test prints. And on shore, they, I don't know the exact number, but let's say eight different prints. And these prints are going to include various, holes or overhangs or some features. And so they have those compared, and they have everything documented on those. So they have the temperature of the environment, they have the accelerometers on the ships, or I'm sorry, on the printers, and then humidity, everything measured, and then they're also recording the performance evaluation with cameras. And so that is the laboratory control, if you will. Now I'm going to do the exact same thing over here on the Navy ships. And so that way I can go in and say, okay, well, here's all my data from the laboratory. Here is the quality of my part. Here's the the inspection of my part. Now I'm going to do the exact same thing over on the Navy ship. Okay, that's interesting. That the pressure was different or the humidity was different. Like it still worked, or hey, it gave me this error. And so that's all things that they're documenting. And really, they're going to do that using what's called digital twins and the metrology or quality control. All right. And so that brings me in a bit to, I wanted to touch on AI and 3D printing a little bit, and apologize, my slides are a little bit off, but that's just from the transfer over to the format. But so quality control, as we're printing it, you can do some interesting things where you have a camera or some sort of scanning device in there. You can use a machine trained model to identify defects, deviations from the design, and really go over any other quality issues. And so what that really translates to is, as it's printing, I can go, oh, okay, I'm measuring this little area here, and it's going to give me an error. It's going to go, hey, this little area right here is messed up. Do we want to continue, or do we want to cancel? And so that saves me so much time and so much waste of material if I do have a bad print, if there was a power blip, if there was, a big wave that hit the ship. So, and then all that data collection, really get into parameter tuning. So I can optimize temperature, speed, layer height, design materials, everything. If I have all that data and it's learning, I can feed it in the quality control data that I scan or use metrology to determine. It can all be connected. It's a great system. So, and then also generative design. So this is more of a forward thinking idea, is that AI is pretty unique. There's a couple CAD softwares out there right now that you can do this. It's called, I think it is just called generative design in some of the CAD softwares. But let's just say I have a bracket. The human mind will think in kind of blocks. So I'll have probably an L-shaped bracket, and I'm going to have probably a triangle bracer in there, or forgetting the word for that. But so that's just, it's a simple thing. But what an AI can do is that it will optimize. So you say, okay, I need it to sustain this amount of force, and it needs to weigh this much. And what the AI will do is optimize the structure and say, okay, because you said it needs to have this much weight, it needs to have this much strength, but it needs to have the bolt hole designs, or the bolt locations in a certain place, it will optimize that. And what it ends up doing is creates a organic shape, which is quite interesting. And what you can do with that is it's a lot of times hard to manufacture, but using that in conjunction with 3D printing, it creates some really interesting designs. A lot of satellites are starting to use that. It's very interesting. So, all right. So I've talked enough about what the idea is and all that, the concept. So now let's talk about what's actually going on right now. All right. So the USS Baton, the Naval or the Wasp class ship named after the USS Wasp, based out of Norfolk. The ship is an amphibious assault carrier, and so the idea behind it is that it has a flight deck and a well deck. So it's almost, for layman's terms, it's almost like a smaller aircraft carrier. And it is used by both they're both Navy and Marine personnel on the ship. So what's good about that is you're going to get Navy and Marine exposure to this 3D printing technology. So there's lots of different components and lots of different systems that both the Navy and the Marines use. The other thing is that it can be used as a enhanced command and control ship. So it can be used as essentially a smaller aircraft carrier in a fleet. And then, yeah, like I said, it was chosen for more research and capability for exposure. And then in 2002, it received the Phillips additive hybrid powered by Haas. So we'll go into what that is. All right, so the Phillips additive hybrid system is a half CNC, half 3D printing system. And how it works is one of the tool heads is actually a 3D printer nozzle head. It's a wire deposition head. So how it works is essentially it's a more advanced automatic welder. And so what's going to happen first is the metal wire, first you have the CAD, and then you transfer that over to the Haas system, and then that turns it into directions for the machine to use. And then it will go through layer by layer and deposit, or similarly, it's very analogous to welding, this system is. And so you can start off layer by layer. It's going to create a rough part, and that's a pretty relative term because it creates a rough part or a green part, and it's relative because that's plus or minus 10 thou. So that's actually could be fine for certain applications. But if you need something a little bit closer in tolerances, the Haas system will change its tool head and then actually go in and refine the more complex shape out of the rougher green part. And then there you go, you have your final part. So this system can actually make quite a high precision part with multiple lasers, and does it all in a system that's already, so really it's an addition to a system that's already proven onto a ship. And that's a great thing to have, in the fact that you need less certifications, you need less training. So it's a really good idea to have this printer on a ship rather than, let's say, a SLS printer, which great product or great technology, but probably not the best for ships. But this one would be great because not only is it already a majority of it is a proven platform, but it prints in 316 stainless steel, and the raw material comes in spools, just like any welder would, or just like any welder would, and it's fed into it, laser melted and deposited into that rough shape. All right. So this has a couple, I wanted to touch on this for this system because it's similar to cold spray in the fact that it has layer by layer deposition. It has good material adhesion and bonding. And then you can also target and repair things. And if I don't get to it, someone remind me that I want to go over a new article I found after I submitted this presentation, that it will touch into this. So yeah, it's similar concept to what cold spray does, but it has a couple advantages in that, and that's structural integrity and material strength, and then design flexibility because it's on a rotating head, and you can machine back, so you can add on material and then machine it back. You get a bit more design flexibility and accuracy and precision. So, and then the other ship that has the metal 3D printing technology on there right now is the USS Essex. So that is also a WASP class. Its home port is in San Diego. So we have one ship on the Atlantic side, one ship on the Pacific side, and then shortly after the USX, the former ship got its 3D printer, this one got its 3D printer. Now it's a different brand, slightly different technology. This is by Xerox, the LMX, and it's described by Xerox as the mini factory in a Connex box. So this was the same unit that was at Naval Postgraduate School in Monterey, California, that I was saying did 2 years of testing with twin part tests. So the Xerox LMX printer, unfortunately, because it is all quite proprietary by Xerox, I don't have a ton of information on exactly how it works, but I do have some, I can't give you very specifics, but the general overview is it's what's called a liquid metal technology. And so unlike other additive manufactured technologies, there's no metal powder, no need for PPE, and really other considerable safety measures. And if you notice, the LMX and then the previous printer both have a lot of answers to the questions that I brought up in terms of how do I integrate this into a ship. So these ones, is there metal powder? No, not really going to be explosive. Is there, am I going to have issues with space? No, they're quite small. Furthermore, you have, they're just overall, they're simple, more contained. All the technology is contained into a small area, and on the ship itself, the machine is actually in a Connex box in its own environment, so it's isolated as it can be. So the LMX prints with aluminum alloy wire. This is quite ideal for marine environments. This one does require a noble gas atmosphere, but as you see, it is in a contained area. So having that gas escape or worrying about PPE issues, it's going to be a lot easier to maintain as it's in its own little secure area. So they claim it's a user-friendly metal AM system. And so the general idea of how it works is wire, just like the previous printer was. This one, the material is wire fed, comes on a spool. So it's fed into a heated reservoir. The metal is melted and falls into the injection chamber. And then I'm sure there's a lot of proprietary stuff in here, but the droplets are ejected and deposited using magnetic fields from an external coil. So pretty cool technology there, but you get some decent parts. So like I said earlier, the objective of these printers is we have the known factors that affect the prints. Temperature fluctuations, electrical fluctuations, stability, but there's also a lot of unknown factors. A lot of times we They were telling me that when I talked to Naval postgraduate school, they were telling me that they expect there's quite a bit of things they have no idea affected the parts. So that's really the whole goal of having these out there. And then to do that, we have the twin experiments. Every possible factor that we can measure is compared to everything we printed on the shore. And then, of course, we're taking all of that and sharing that with our partnerships and institutions out there. So yeah, we're learning from others' success and failure stories. So I touched on this a little bit, but I'll go a little bit more into depth of it. So why were these printers chosen? So there's many different 3D metal technology out there. But why were these two are kind of similar? They had some key differences, but they both avoid powderized metal. Like I said earlier, that's a very popular technology out right now. They use that all sorts of different applications and industries, but it is true that it avoids the dust. You can contaminate the materials fairly easy, and avoids explosions and fires. So at this point, the print volume is not gigantic. It's really more for the small part replacements in the future. Maybe, let's see. But it's not really designed for large scale. But I believe the idea is let's focus on the small scale, then we'll work our way up. They're both more or less self-contained. They're avoiding, as much as you can, they're avoiding the harsh environment of the ocean. A lot of these are readily, or both of these are, the consumables are readily available. It's metal wire. So this, I mean, I'm sure we could go to a welding supply store and pick up very similar, if not the same, raw material. And so that would be very easily accessible on land if you do need to resupply that raw material. And then they're really off the shelf printers. So that means that uh, they have a whole company behind dealing or inventing them. So really other companies can buy this and then, make their own determinations and certifications and stuff like that. And then a reduction of PPE. We're not adding on very much, if any, safety precautions or requirements, or it's user friendly, as Xerox says. So we're not necessarily going to be needing that laboratory setting like I talked about at the beginning. And then we'll talk about the future impacts of this metal AM. So enhance naval readiness, hot topic. So reduce downtime for maintenance. I'm going to have those parts available to print anytime as long as the machine isn't busy. Quick replacement of critical components and print components at remote locations. So like I said, if you're out on a patrol or a mission of some sort, you could, if a critical component fails, you're going to have to turn around or have some sort of supply ship come up and reach you. That's going to affect readiness. But if you can print it hypothetically and replace it there, that's going to save a lot of time and critical readiness. And supply chain resilience, so reduction in lead times. And we're talking lead times in the scope of being out in the open ocean. If I could not produce this in a traditional CNC, reduce dependency on traditional supply. We talked about that. And then, on-demand printing capability, rapid prototyping, customization. Let's say, okay, maybe it's not just for replacement parts, it's more so for rapid prototyping. And so engineer on the ship or engineer even on shore could design something they want to test, send it via satellite, shows up on the ship's computers, 3D print that right then and there. And then down here in complex geometries and lightweight structures, that opens up a whole new avenue for non-traditional manufacturing to optimize geometric shapes. All right, so that kind of concludes everything I was talking about. So yeah, do you have any questions?
Great, thank you so much, Matt. What an informative presentation. So we have a handful of questions coming your way. So there's a couple in the chat, a couple in the Q&A. So I'll start reading them out and then you can go from there and answering them. So the first one is, what is the largest metal part you can print?
So the largest metal part you can print, that is, I guess it's up to your imagination. No, really what it is I don't really, the largest metal structure that I've heard of someone printing is a guy called, I think it's Big Metal Additive, and he is attempting to make satellites, like satellite chassis. And so those can be pretty big. They could be, you know, size of cars or something like that. Or there's another company out there that does the, is it the fuselages? I believe it's, the term is the fuselages for the, like the structure of the satellite boosters, I guess, the fuel, whatever holds the fuel in the rockets that go up to the satellites. So that one is, it's essentially really just a welder on like X, Y, and Z axis, and then they computerize it and it prints it, the whole thing. So I mean, really, it's to be determined is the largest thing. So I've heard of things pretty big, as big as satellite rocket engines.
Okay, next one up is, can you supply a list of the top 5 to 10 companies that do contract metal 3D printing of small and large parts?
I don't have that on hand. So I mean, I assume that is more, I know RPM Innovation does that. That's the one I just thought of offhand, but I can certainly look into that more. I just don't have that offhand to give you a list of that. Yep. So there's quite a bit of companies out there, though. There's a few of them. 3DEO is a cool one I've talked to before. And they, in my opinion, are really doing some of the first mass production 3D metal printed parts, and they make small little parts for guns. Pretty cool stuff. So there's a lot of companies out there. Yeah, if you give me your email, I can give you that.
Yeah,
Sorry.
I was gonna say, would it be okay if they just shot you an email? This is coming from Mr. Bob Diamond. So I would suggest
there's my email there.
Yeah. Next up is, what percentage of Navy ships are equipped with traditional CNC manufacturing capabilities?
What percentage?
Yes.
Traditional? I believe it's more or less standard on most resupply ships, or really any larger ship that's going to have complex systems or material. So it's quite a bit. I don't have a percentage, but I believe it's fairly common, or some sort of manufacturing capabilities. CNC, I would imagine quite a bit.
Can you provide a rough order of magnitude for cost of one of these AM systems?
One of these AM systems. So these particular ones, these are all through sales. So I did not reach out to sales to find a value, but I do know similar systems for Metal X, for example, a little bit different of a technology, but they're in the range of about like 150K. But I would have to guess that these are a bit more.
Is the in-orbit ISS doing any metal 3D printing?
So they're not doing any metal 3D printing, but it is a great, and this is why I touched on earlier, is that it's a really a joint effort between the different DoD and sharing all this information, because yeah, I guess let's put these things out in the most harsh conditions and see what happens. And that's a lot of the ideas that we're gaining, but that would be a fantastic idea to have that on satellites, or, you know, think about it on Mars one day. Like that's a great idea. And like, we're going to learn a lot, so much from how do these things behave in harsh conditions. So not right now, but certainly I would think that they are planning on it. It's a good idea.
Next up, how successful have you been at establishing material strength allowables for the various machines and materials to ensure proper margins of safety for the finished AM parts?
So that is a very loaded question there, because that kind of touches into what I was talking about, the standards, and it is a very broad topic. And I'm not trying to avoid it, but it's just it's there's so much to it, because if you really want to, when you're 3D printing something for a replacement part, the idea is that, okay, I want to have all the at least as good of strength. And certainly some of the powder 3D printed, like some of the powder metal 3D printing stuff, have like touched equal or surpass the strength. But others, it kind of comes down to almost a philosophical question here, is that is it better to replace a CNC? Like, why are you replacing that CNC part with a metal 3D printing part for the sake of it? Or should I redesign that part to optimize for 3D printing? And then it's like, did I really need that strength to begin with? So it's a complicated question. So I mean, I'm not necessarily involved in like, this is more of a hobby for me, researching this stuff. So I'm not involved in any of the certifications and stuff like that at this moment, but I do know quite a bit of people over at NIST. NIST would definitely have answers to those questions, NIST. So they deal with a lot of the standards, and they deal with a lot of the strength requirements and ideas behind that kind of applications. So yeah, I would research that with some of the standards, and of course you can all send me emails afterwards, and I'll try my best to give you any answers or point you in the right direction.
Can you clarify the differences between Metal X and desktop metal, and why these machines are not used on the ships?
So the differences between them, as far as I know, they are fairly similar parts. And so for those who don't know, the Metal X and desktop metal use a different kind of process. And so how it works is, basically you have a green part that is printed like a traditional, you have a powder that is suspended in a polymer filament, and then that's printed about 30% larger than it actually is, and that's your green part. Then you do what's called sintering, and that will melt away all the plastic in there, so you're left with like kind of a metal lattice that's a bit larger. Then when it gets sintered, it will shrink, and then that will be the more or less correct dimensions of the part. So it's kind of like a powder forming, but anyways, yeah. So why those were not incorporated on the ships, I don't really have an answer for that. I believe I'm sure that's has to do with contracting and politics maybe. But the real, I mean, I think both of those printers and that technology will be quite viable on a ship. The only thing I can imagine is that if you look at the Xerox and the Philips system, it's all contained in one unit, but then the Metal X and the Desktop Metal, it's like 3 different like 3 different components that you have to like put it in. So maybe that has something to do with it as well. Like you have the printer, and then you have the oven, and then you have like the wash tank and so forth. So I would assume that could be a factor, but for the exact reasons, I am not quite sure, other than talking to the contracting people.
Okay. We have quite a few more questions, so we won't be able to hit all of them, but I'm going to try
Okay,
to
I'll try my
few
best.
more. Yeah. The next one is saying that you mentioned structural integrity and strength. What testing and comparative performance occurs with AM parts and OEM parts? And in such an instance, what part performance standards are used?
So, yeah, like I said earlier, there's really no all-encompassing standards and testing procedures for the metal AM, and it has to do with the non-homogeneity of the 3D printed, just the concept of it. So as far as my research in the past has concluded, is that in terms of how the industry does it, they have their own internal qualifications that the majority of companies that actually manufacture 3D printed parts or have a system that they use 3D printed parts on, they have their own internal private system of what they do. So unfortunately, they keep that pretty close because it's they spend a lot of money and effort into getting that, and then also they use sorry, they lost my train of thought. So yeah, they have their own testing as well. So it's very proprietary for them. But there are some standards being made for exactly how you test all that stuff. But really, the answer is it really depends. As of right now, the long-term goal is not to have that. They want that standard, like normal OEM traditionally manufactured parts, but it's so case by case on a lot of them. It's difficult to say, yeah, this is the testing that we do for all the parts, and every part you have here, you do this testing. It's kind of hard to say with that. So that's why, I mean, it's a whole nother presentation to go into exactly why or exactly how the testing is done. And I actually did write a short article about that. Yep. So you can look that up on the website here.
Okay, next up we have, what is the current interest in implementing larger print volume systems like a DED system?
Like the DED system. I'm not familiar with a DED system, but I would, my interpretation of that would really, they want to start small as of what the Naval Postgraduate School, during my interview with them, that's what they told me, is they want to start small. So I don't think we're going to have 3D printed warships anytime soon. It's very hard to, you're going to have more trust in a traditionally manufactured ship because there's so much volume in that. And let's say exactly what I was saying earlier is that, hey, power blip for 1 second during that 1 month, 3D print that it took to do this whole thing. Well, that's a void that's extremely hard to detect unless you X-ray scan the entire aircraft, or you have some sort of standard or AI that's going to tell you that you had that. So implementing them for building ships, I don't think it's anytime soon, but definitely check out the The name of the company that 3D prints the fuselages for the rocket boosters is escaping me, but Big Middle X, it's a cool one. Check them out. And so there's definitely interest in it, but I know I hate to keep going back to it, but it really is a idea of standards and testing requirements, which are not, there's no overarching ones yet, which really make it hard to be like, yes, we're going to 3D print this, but it's like, okay, you really have to internally develop your own procedures. That's the tricky part as of right now.
Can you identify what the digital twin for a 3D printer system should consist of?
So the digital twin, let me just go back to this. All right. So the digital twin, how it works is you're going to have let's say I start off with a CAD. I'm over here in the initial design area. I start off with my CAD. I design it, engineer designs it, whatever. And then it's going to go into another program system. And like that individual part is going to have a serial number, and then that digital twin is going to follow it throughout its life cycle. And so we're going to start out with initial design. All right, so I have my CAD there. That's what it's supposed to be. My digital twin shows the CAD, and then 3D print it. I have my physical, I'm sorry, not 3D, well, sure, 3D printer or manufacturer, however we want to do it. And so I'm going to, let's say it's 3D printed. So I'm going to have that physical piece there. It's going to have a serial number on it. I can look that up on my database. And so, okay, it printed with these parameters during this time frame using this batch of raw materials. And I'm going to do metrology on it. I'm going to measure its all of its components, give it some sort of report on that. That's going to be included in the digital twin there. I could do some analysis based on that. That's going to be included on there. And then let's say I'm going to do rework in 5 years or something. And so I'm going to do inspection on it, NDI inspection, going to make sure there's no voids or make sure there's no, issues with it or cracks. Then that's going to be carried on into the digital twin. So and then finally, it's time to replace a part. It's over its life cycle. And that is going to be noted in the digital twin database. So it's quite a bit of information you can get from your digital twin. So it's really a full life cycle kind of deal. And then you can compare that to one, on the ship.
I'm going to pick two more. If I don't read out one of yours and you're still on, I'm sure that you can email Matt separately and he can kind of speak with you offline, but I just want to be mindful of everyone's time and try to stick to our hour time frame. So another follow-up question for this about kind of the digital twins. What kind of lessons have been learned from these digital twins or simulations versus what was found in physical testing?
So that's what we're all doing now. That's what we're all doing now. So, well, not me, but Naval Postgraduate School and the rest of the DoD. There's not any active information or lessons learned that I'm aware of as of right now. Like this is new within the last year that they actually put these on the boats, on the ship. Sorry. So it's all very new.
One is, how strict are requirements for noble gas atmosphere for the Xerox LMX printer? Would lab grade noble gas need to be restocked or generated at sea to supply that system?
That I don't know offhand. A lot of what I found regarding the LMX printer is it's all quite proprietary. Like for some reason they very much hold on to any of the information. I mean, I'm sure if you buy them LMX, you can find that out. But just in my research for doing this presentation, I was not able to find any very specific details like that. So, but LMX has some great videos on YouTube. Definitely check them out. And then, which I wanted to show in here, but I ran out of time. But yeah, so Xerox by LMX. I'm sure there's more information out there, but for this presentation, I don't know the exact atmospheric conditions, but I would assume it's very similar to a standard welder, like a MIG welder. So that would be my answer to that, because it is in theory a similar process.
I'm going to make this our last question. And can you speak to any of your experience in dealing with the property rights aspect?
Property rights, I would assume that's like
IP.
intellectual property.
Mm-hmm.
So dealing with that, in my experience, is essentially like there's many websites out there for, I want to print a figurine or something like that. You can go on their websites and there's licenses, and you can pay for those licenses, the models, and then generally you have the ability to print them, not sell them. Some other things you have the ability to print them and sell them. That's more of the DoD. I'm sorry, that's more of the commercial side of things. Is that it's a question of, is the owner going to give you full rights on it, versus if you have to pay for that one, it's very strict. But in terms of actual intellectual property on like something for the DoD, you can do reverse engineering on parts, and then you can print it. I know you can print it or reproduce it for personal use, but for if you're manufacturing it or selling it, that's essentially the same as stealing the drawings and 3D or manufacturing your own part. So that's probably where you would have to draw the line. So, and it probably comes into if you're selling it or if you're selling products for a part. So, yep.
Okay, well, great. Thank you so much, Matt. I know there's a handful of other questions there, but I want to honor our time. So those of you, if you're still online, if you can please email Matt your questions. I'm sure he would love to chat with you offline about this. This was a wonderful presentation, very informative. I learned lots of new things, so I'm sure everyone else did as well. So thank you, Matt, for joining us. Everybody else that joined us as well. You can see the slides. They'll be on our dsiac.org website, on our webinars page, and we'll also upload them onto our YouTube channel.
Great.
Any last parting shots, Matt? Yeah.
No, just thank you so much for joining me. And yeah, I'll try to get to your questions. Email me or put in the chat, or yeah, thank you very much.
Wonderful. Well, have a great day, everyone, and hopefully we'll catch you at our next webinar.
All right. Thank you. Bye.
Bye.